In this video, we're going to go over how to design ChatGPT. This is a question you could expect in ML system design or LLM system design in interviews in places like AI engineering or ML engineering roles. So what we're going to do is we're going to walk through the key points that you want to be able to discuss in order to walk through this problem comprehensively. In order to approach an open-ended case like this, you have to think about how you're going to constrain the problem. To do that, you have to discuss the functional requirements and non-functional requirements. The functional requirements are essentially the qualitative aspect of what is the output that the model or the system should do. The non-functional requirements are the quantitative metrics. So the functional requirements for the ChatGPT in this case is, simply put, the user sends some sort of a prompt in a form of text, and there's an agent or AI service that will provide an intelligent response. The second thing that we want to establish is that the interface itself needs to be able to handle some arbitrary documents, so things like the CSV or PDF or any files that the user may want to ask questions about. The third aspect is that you want some sort of a real-time search capability. So that means that the agent has access to the World Wide Web, thereby it's constantly updated with the latest information. The fourth aspect of this, you want to ensure that there's safety check and it prevents any kind of toxic content from being projected onto as a user output. And last but not least, you want to be able to persist the user chat history. So if the user started with the name, "Hi, I'm Dan," and then goes on about having that conversation, and later down the road, the user asks, "Hey, what was my name?" If the agent forgets what that name is, and it's a little bit embarrassing. So somehow we need to figure out a way to persist the history. And what is not in scope for the sake of this case is, any kind of deep search capability or multimodality capability. These are some additional questions that the interviewer may ask as a follow-up. But for the sake of this open-ended case, we're going to constrain it down to these 5 that really matters to us. Now, when it comes to non-functional requirements, generally speaking, what you want to talk about are these 3 different aspects. So you want to discuss the concurrency in a given point in time, how many requests could be handled, managed by the service, in which case our rough estimation is 1,000 concurrent requests based on the expectation we have about 10 million daily active users. And we also want a service that has low latency. So that means that in some sort of a time frame, we want the service to be able to provide a full response. Now, this is not like the Google search where you want a 200 or 300 millisecond response. It's just not feasible. It takes time for the agent to process the information and stream that information until completion. So ideally, what we want to look for are 3 seconds to 10 seconds. So P95 response time being 3 seconds and P99 response time being 10 seconds. And we also want a high availability service. So that means that the service is constantly online 99.9% of the time without any downtime. Now, with those requirements in mind, the next thing that you want to talk about are the architecture design. So when it comes to the design aspect of this, first and foremost, let's just start at a very high level. Essentially, what you want is that the user sends some sort of a prompt, kind of like what you see right here, where, write me an essay about the history of basketball. And so the user sends a request through this interface, right? And then this prompt gets injected into the backend API. And you can think of this as an application server in general. Anytime you have any kind of service, typically you have the front-end client and then you have backend API. And then there's all these set of different application logic that will handle this. So right off the bat, this client, the backend, simply does a chat service. And then you have a dedicated service, an agent service that handles any kind of logic that deals with how the prompt should be processed in order to generate that response. So this is at a high level what our service should be achieving, right? It receives this text-based type of input, and sends a response in some form of a text, image, or whatever multimedia form that the user has prompted the service to do. Now let's delve more into the agent service itself. What does it actually mean? So when you think about any kind of agent in general, what it essentially means is that instead of just having a single LLM component that will take the input and output, there's some level of autonomy in terms of what the agent can do. And in order to achieve that autonomy, you need the following components. You need something called tools. Tools are essentially any kind of API or databases, any sort of external components that the agent can access in order to provide some sort of a result that the user is wanting. And it also needs an ability to think. What that essentially means is a logical framework of how the agent should be solving a problem. And a couple of frameworks that are predominant are something called chain of thought. So it's a series of input and output of some sort of a self-reflection mechanism performed by the LLM in order to get to a final response. And then you have something called react, which is reason plus action. And what that essentially combines is a chain of thought followed by some sort of an action in order to gather observation. And then that series of iteration helps agent converge toward the final solution. And you also need something called memory. And what memory essentially does is it just simply stores any kind of in-session user interaction on the chat service itself. So with that in mind, something that you want to talk about is what is the actual logical framework. Instead of just having a single input, a single call to the LLM for inference or to get the response, there's a bit of a back and forth exchange between the agent service and the LLM. And so this type of framework is what you call react. So it's called thinking, acting, observation, followed by some sort of an iteration. So thinking essentially is a series of chain of thought. Think about how you might solve a problem that involves mathematics, like maybe solving an integral or something like that. You have to first of all try to recall the logic of how do you integrate a following formula, and then you have to think about what is the underlying calculation in order to integrate a formula, and then you might double check the answer. So same thing, there are multiple calls to the LLM that is happening before you get to the final answer. But oftentimes chain of thought has some propensity to hallucinate. So it needs to form some sort of an action followed by an observation in order to see some intermediary result before it converges to the final solution. So for that to happen, you have to do something called action. So let's suppose that we're going to trace this logic here. Don't think about this agent service as a separate LLM or anything like that. What it simply does is that it's a way for the LLM to interact, or it's embedded within this agent service, and it just simply interacts with any kind of tools or application logic for the LLM to perform action, get the observation back and forth. And so suppose that the user has posed a question, what's the latest news about the economy? What the LLM is going to do is, instead of just spitting out an answer and then that gets sent back to the user, LLM is going to have an internal chat itself, kind of like what a human does, where it's going to try to understand, okay, well, based on this question, I don't have the latest information about the economy. Maybe I'm a little bit outdated about this. So perhaps there are some tools I can leverage as a way to get the latest information. So the LLM is going to see within this overall service, what are the tools that are available. And then the service is going to send back some set of tools that it has available. So sort of like the search API or any kind of database. The LLM will take that information and then make a decision, a choice on which tool it needs to use in order to answer the main question, which is about the economy. So for that to happen, what it's going to do is, okay, well, it's going to see that, all right, I need a search API because obviously I need to be able to browse the latest information, maybe get some news or something like that. So it performs an action to get more information about how to use the search API. The agent service will go ahead and send some additional documentation about this API. Then LLM will, after reading this information, will interpret how to actually generate a valid API in order to get the information that it needs. So it gets the following information, which is about, let's just say the federal interest rate. There's constant variability that's happening with that. And so it gets the latest information about that. So the LLM will now use this information to provide a final response. So it goes through this series of iteration in order to get to the final solution. And this is what we mean by React framework. And that's one of the core mechanics in order to build a ChatGPT-like service. So with that established, let's go back to the architecture overview. So something that you want to know is that the agent service, you want to do some additional decoupling here. So you have to keep in mind that oftentimes you're going to be utilizing some sort of external tools. And so in order to do that, you need something called retrievers. Depending on the different frameworks or different providers, they may use something called tools. Tools or retrievers, you can kind of think about it as a little bit synonymously. But essentially what it means is that it's a connection, it's a connector between these external data sources to the LLM that is able to access these services. A retriever is essentially just connectors. It's some sort of like a script that helps you establish that connection to maybe a database, to maybe to Google or Bing, any kind of browser services, or even to some kind of documents. And these are optional. It's not the case that anytime you have a prompt, the service is going to, by default, use any of these connectors in order to get the information. In some cases, the LLM itself will just be able to generate a response right off the bat. So let's do some additional decoupling about this. Something that you want to think about is how do we actually store the user memory? So that was one of the requirements for us, which is that we have to be able to store or cache the user history. And so part of the core component that we're going to need is some kind of a memory. And I'm going to elaborate a little bit more about this. And what that essentially is a caching layer. So within the given session, as the user and the agent is having a back and forth conversation, that each message in that given thread gets cached in that memory. And so anytime the user exits that session or comes back to the same session, they want to continue to have that conversation, that information can get readily retrieved. And so you can have a continual conversation without the agent completely forgetting about what had happened couple messages ago. Now, currently, what is missing about this architecture component is that when it comes to ChatGPT-like services, you're often going to have redundant queries. So maybe another user or the exact same user may pose the exact same question at the same time, which is, what is the economy as of right now? And if that's the case, you don't want the agent to go through the series of logic, which is computationally exhaustive, considering that, you're going to have millions of users with a lot of concurrent requests. So you have to think about a way to offload that in a more intelligent manner. And so what you could do is you could have something called semantic caching. And what that essentially is that if there's a query where the response has already been generated, you simply just cache that. And so instead of going all the way through this agentic logic, rather than that, it just simply retrieves the same information for the query that has already been seen before from the caching layer and then send it back to the client. That's a way to save costs, to reduce the load on more computationally exhaustive processes. Now, the next thing that you want to talk about is how do we handle document uploads like PDF files and stuff like that. So the way we do this is we need something called the vector store. And there are a couple of components that need to be in place in order to handle uploads for PDF or any kind of documentations that maybe the user wants to have a chat about. To do that, you need a series of logic. We can have something called like a parser API. So it's essentially an add-on, an extension of a different type of application service, where when the user decides to upload a PDF documentation, this parser API will go ahead and chop this document into multiple pieces. So instead of just simply ingesting the entire document on some sort of vector store, it is going to chop it so that it's easier to search. So once you chunk these documents, what you have to do is you have to go through an embedding model. And what that means is that you can't just store a text into a vector store. You have to do some sort of a conversion. You have to be able to represent that text into a vector, which is a dense numerical representation of a piece of a document. An embedding model can help us with that. So for each piece of the document, you input that into the embedding model, which will convert that into a dense vector, and then you'll have an ingestion service, which will take the embedding along with metadata about that document and ingest it into a vector database. Now, the more deep dive conversation on the mechanics of how the vector store works is out of scope for the sake of this video. But just understand that vector store and building any kind of agentic service often go in tandem, so it is not something that you want to ignore. Once you have this set up, once the user uploads the document and then from there asks any kind of question, maybe they've uploaded things like 10K or 10Q SEC filing, PDF file. So, and the user may want to ask stuff about, the company's financials. Then the agent will go ahead and use a retriever that corresponds to the vector store, fetch that information, and then use that along with the initial user question to generate a response. Now, one final aspect to our requirement is that we want to keep our content safe. We want to keep the user safe. And how do we go about achieving this? So we're going to need a separate service, which is like a moderation service. Think about any kind of toxic classifier. These are essentially a separate set of models that will take any kind of user inputs and the outputs from the agent service itself. And it's going to ensure that there are no PIIs, maybe like users, SSN or emails, any kind of sensitive information are filtered out. And it's going to look for any toxic, bias, or harmful content from being rendered to the client. And so this moderation service will work in tandem, and it can function in both on the receiving side. So just before the user's prompt gets sent over to the agent service, and then after the agent has generated a response, it will pass through the moderation service before it's sent back to the client. So all of these are the components that will help us build a ChatGPT-like service. Now, walking through the architecture overview doesn't provide the thorough response that the interviewer is going to be looking for. Either they're going to ask some follow-up questions, or that you're going to have to pick out some topics and do additional exploration. And something that we can explore are, what is the actual LLM or the large language model? What does it actually consist of? How is it actually trained? There are three key components when it comes to building out a large language model. First and foremost, you need something called a supervised fine training. And what that essentially is a transformer model. We're not going to talk too much about the underlying mechanics of what the transformer model is, but just understand that one of the core components of the transformer model is that you have something called an attention mechanism. It's essentially a way for a model to understand the context and the relationship of words. And so this is one of the core components in order to build out a LLM. And so first thing that you want to do is you want to do something called a supervised fine training, where you're taking this transformer model and you're going to train it on a large corpus of textual data, where you're constantly trying to train or predict the next word or the next token in a given text or document. Once you have the underlying transformer model that is trained on a large corpus of data, from there, you're doing some additional fine-tuning. So maybe you're doing some sort of a sentiment classification or getting it to answer multiple choice questions based on an input prompt. It is essentially a fixed set or finite set of responses that you're training the model on. So by doing so, it's able to extrapolate or draw some initial set of inferences about the input text. Then from there, you have in the next phase in this process, which is training a reward model. And what that essentially means is that you have a separate model that is now going to grade the response from the main model. In order to train a reward model, how this actually works is that given the input, you're going to generate multiple variations from that LLM. And the human reviewer is going to rank order the response based on the quality. And the reward model is going to learn that type of ranking. And so now what we can do is we can use this reward model as a way to self-train this mechanism where you given the input, you have something called a PPO model. So it's that is a reinforcement learning layer. Generate a response. The reward model is going to score that response, and then it's going to be fed back into the PPO. And this self-calibration happens as you optimize a policy that is ultimately going to maximize the reward based on the type of output that it's actually generating. So this RLHF framework serves as one of the bases to the large language model that we're seeing across many of the services as of right now. Now, one of the fundamental aspects of walk through these type of ML cases is that you want to discuss metrics. There are two sets of metrics that we want to be cognizant of: offline metrics and online metrics. And when we think about offline metrics, we can think about perplexity score. So this is a measure of how well a model predicts tokens. And there are some set of metrics that we can be cognizant of. So things like the rouge, blue, or meteor. This measures the level to which the model is able to summarize well. And we can also measure for F1 score for any kind of questions and answering task. We can also get reviews from the humans themselves. Of course, these are sort of like mechanical Turk, and they're pretty expensive, but it also provides the input from the human for us to be able to evaluate the model. And last but not least, we can have something called a reward model score. So this is like the AI or LLM as a judge, sort of like what we see in the RL framework. And we're using this as a way to first and foremost evaluate the LLM performance. Then we need to be able to measure how this actually performs once it has been integrated into the application like ChatGPT. And the online metrics that we want to track are things like the user ratings, so thumbs up, thumbs down, stars, session length, the user retention, session retention, task completion rate, and then we also think about some software metrics, things like latency and response time, the P95 and P99. Now, one thing that you want to talk about is model inference. So going back to one of the requirements for us is that we have to be able to handle large volume of load, and we want low latency. And how do we go about achieving that? And that is by achieving some additional optimizations with the inference themselves, because generating one token to the next is a very computationally exhaustive, expensive process. There are three strategies that we can employ that can help us with this. So first and foremost, we can do something called model quantization. You can think about it as a way to just compress, instead of having a high precision floating point, which is memory intensive, you can reduce it into a low memory usage, something like integer 8 data type. And this is going to reduce the memory usage, and it's going to speed up the inference. The second strategy that we can employ is model pruning. And you can think about this as like a regularization method, where instead of trying to utilize all of the parameters, you're filtering out the ones that are not relevant and only focusing on the attention heads that are actually going to produce the type of quality response that you're looking for. By doing so, you're able to reduce the computational load. And the third strategy is something called key value caching, sequence of tokens that has already been processed. Instead of redoing the computation from scratch, you're simply just reusing the previous attention state as a way to generate the response. By doing so, you're avoiding any kind of redundancy when it comes to generating inferences, thereby speeding things up. So these are the three strategies that we can employ in order to speed up our model inference. Now, last but not least, let's talk about the deployment. So the deployment is going to vary based on the service providers that you're comfortable with. You can think about some major providers like GCP, Azure, or AWS. For this case, what we're going to go through is how do we actually integrate this on a provider like AWS. Now, first and foremost, what I will say is that when it comes to these application logic, there are three services that will come up again and again. These are going to be EKS, Lambdas, and SageMaker. We're going to be using services like Elastic Container Service, or which is a self-managed Kubernetes service that will auto-scale container applications. And now, one thing I'll note is that for the retrievers, so these connectors, we're going to be once again using Lambda functions. But these do not have to be online, and the state do not have to persist 24/7. It's more of an on-demand usage, in which case we could be using AWS Lambda in this case. For any kind of storages, so we need to be able to store some user session history. So we're going to use two types of storage here. So for any kind of short-term storage, we'll use Redis. But any kind of long-term storage, we can use a database like DynamoDB, which is a non-relational database. Now, these retrievers are connected through these external services. So for any kind of data set that perhaps need to be retrieved, depending on the nature of the data, it could be Dynamo database or it could be Aurora. Aurora is a AWS relational database. And for vector store, you can use providers like Pinecone or Weavid or Quadrant. But if you were to go with the option that AWS has, that would be something called OpenSurge. So the combination of these services are what is going to allow you to host a ChatGPT-like service on AWS. So there you have it. These are the core key points that you want to walk through when the interview question is about how would you design a ChatGPT-like service.